Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. Here are the three given column vectors, S1, S2, and S3. We'll combine them to form B. The task: compute B equals 3 times S1 plus 4 times S2 plus 5 times S3. Rewrite that as Sx equals B, and then compute the row dot products that give B's entries. Think about it. Can you figure it out before we proceed? You may pause for a moment to ponder. If not, you'll feel good learning it soon. First, we form the linear combination and compute each entry of B by adding the corresponding components. The first entry is 3 times the first component of S1 plus the others. That gives 3. The second entry adds 3 and 4 to give 7. The third entry adds all 3 coefficients to get 12. Putting those entries together gives B equals the column vector with entries 3, 7, 12. Next, we express the same linear combination as a matrix times a coefficient vector, following Strang's observation that a matrix times X is a linear combination of its columns. Let S be the matrix whose columns are S1, S2, S3, and let X collect the coefficients 3, 4, 5. Multiplying S by X reproduces the linear combination and yields B. Remember, each column of S is one of the S vectors, and X's entries are the coefficients we used. Finally, we see Sx as 3 dot products. Each row of S dotted with X gives one entry of B. Row 1 of S dotted with X picks out the first entry, 3. Row 2 sums the first 2 entries of X to give 7. Row 3 sums all 3 entries of X and yields 12. Those 3 dot products are exactly the entries of B, confirming Sx equals B. Quick recap of what we did. Step 1. Compute the linear combination to get B equals 3, 7, 12. Step 2. Assemble S from the columns S1 to S3 and X from the coefficients. Sx reproduces B. Step 3. Each row dot X gives one entry of B, confirming the matrix vector product viewpoint. Nice work. Stay curious and watch the next video to learn more. We promise it's fun. Yes, it's fun. Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. Here's the matrix S. Notice its ones build up along the lower triangle. And here are the unknown vector Y and the right-hand side B we want to match. The task is to find Y so that Sy equals B. Pause and think. How would you use the structure of S to make this easy? If you don't know yet, you'll feel the satisfaction of discovering it soon. Break S into its 3 column vectors S1, S2, and S3. These are the building blocks for B. Writing Sy as a linear combination, B equals Y1 times S1 plus Y2 times S2 plus Y3 times S3. Entry-wise, the linear combination gives a simple lower triangular system. B1 equals Y1, B2 equals Y1 plus Y2, and B3 equals the sum of all 3 Ys. From the first equation, we immediately get Y1 equals B1, which is 1. From the second equation, subtract Y1 to find Y2 equals 4 minus 1, which is 3. Finally, the third equation gives y3 as 9 minus the sum of the first two y's, so y3 equals 5. Putting the entries together, the solution vector y is 1, 3, 5. Think of S as computing cumulative sums. Each B entry is the sum of the Y entries up to that position. Inverting cumulative sums gives the first differences formula. Each Y is a difference of consecutive B's. Applying the formula to the numbers gives Y equals 1, 3, 5, the differences of B. Let's recap the short key steps. First, we wrote down the column vectors of S. Then we solved the lower triangular equations by forward substitution. Finally, we recognized S as cumulative sums and inverted it by taking differences. Thanks for watching, and hey, stick around for the next video to see more clever matrix patterns and tricks. Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. Here is the matrix S. Notice it is lower triangular with 1s on the diagonal. And here is the right-hand side vector C and the unknown vector Y with 3 components. We are given a lower triangular matrix S and a column vector C. We will solve SY equals C for Y. Write Y as S inverse times C, and determine if the columns of S are independent. Pause and think for a moment. If you don't know the answer yet, you'll feel the satisfaction of learning it soon. Look at the first row. It reads Y1 equals C1, so immediately Y1 equals C1. The second row gives y1 plus y2 equals c2. Substitute y1 equals c1, which yields y2 equals c2 minus c1. The third row sums all 3 unknowns. Substitute the earlier values for y1 and y2, and simplify to get y3 equals c3 minus c2. Putting the pieces together gives Y as the column vector with entries C1, C2 minus C1, and C3 minus C2. This is the inverse of S. Multiplying this inverse by C reproduces the Y we found. Here's the multiplication showing S inverse times C equals the Y vector we computed. Because S is lower triangular with 1s on the diagonal, its determinant is the product of the diagonal entries, which is 1. A non-zero determinant means S is invertible, so there is a pivot in every column and the columns are independent. Summary of what we found. First, the inverse of S is this lower bidiagonal matrix. Second, the solution Y is C1, C2 minus C1, and C3 minus C2. Finally, because the determinant is 1, S is invertible and its columns are independent. Thanks for watching. Watch the next video to learn more and maybe see how this structure generalizes. It's surprisingly fun. Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. Matrix 1 depends on C only in the 3-3 entry. Matrix 2 has C in the first row, third column. Matrix 3 has an entire first row equal to C, C, C. We are given 3 3x3 matrices that depend on a number C. For each matrix, we want the values of C that make the 3 columns linearly dependent. Think for a moment. What test do you remember for column dependence of a square matrix? If you don't recall, you'll enjoy learning it here shortly. Start with matrix A1. For a square matrix, columns are dependent exactly when the determinant is 0. Expand along the first row. The third term vanishes because of the 0 in the first row, third column. Compute the two 2x2 minors to get 2c minus 4 and 3c minus 7. Combine the minor values to get det A1 equals minus c plus 3. Set the determinant to 0 and solve. So for matrix 1, c equals 3 makes the columns dependent. Now A2. Again, columns are dependent exactly when det A2 is 0. Expand along the first row. The middle term drops out because its coefficient is 0. Each 2x2 minor equals 1, so determinant equals 1 plus c. Setting the determinant to 0 gives c equals -1, so that value makes the columns dependent. Quick recap for matrix 2, c equals -1. Finally, a 3 has the entire first row equal to c. We'll expand along that row. Because each entry in the first row is the same scalar c, each cofactor is multiplied by c. Compute each 2x2 minor. We get -9, -3, and 3 respectively. Substitute the minors, simplify the combination, and factor out c to get -3c. Set the determinant to 0 and solve to find c equals 0 for matrix 3. Let's summarize the c values that make each matrix have dependent columns. Matrix 1 is dependent exactly when c equals 3. Matrix 2 is dependent exactly when c equals -1. Matrix 3 is dependent exactly when c equals 0. Nicely done! If you enjoyed this determinant detective work, watch the next video to explore more linear algebra tricks and fun examples.